Modern medicine has achieved something remarkable. It keeps us alive longer than ever before. But that success has created a medical paradox. Because total lifespan has increased without halting the biological aging process, we now spend a drastically larger portion of our lives in a state of physical decline. The loss of our physical independence is driven primarily by two physiological conditions. The first is sarcopenia, which is the severe age-related loss of muscle mass. The second is sarcopenic obesity, the continuous accumulation of fat as we age. Together, these conditions quietly dismantle our autonomy. As muscle disappears and fat takes its place, basic daily activities, like standing up from a chair, walking upstairs, or holding a steady posture, become increasingly difficult to perform. The ultimate objective of longevity science is eliminating the decades of physical decay that precede the end of life. To solve this, scientists have tested a class of anti-aging compounds called geroprotectors. In laboratory settings, these molecules successfully extended the healthy lifespans of simple organisms like yeast and roundworms. But researchers continually hit a biological wall known as the translation gap. When these exact same chemical compounds are tested on complex mammals, they almost universally fail to replicate the results seen in simpler animals. A viable intervention for humans requires a compound that actually works in mammalian biology. Crucially, it must be effective when administered in midlife, when the actual symptoms of decline begin, rather than requiring a lifetime of preventative daily dosing. Two specific molecules have emerged as viable candidates for this exact task. This is pyrroloquinoline, or PQQ, and its closely related derivative, imidazopyrroloquinoline, or IPQ. Both are naturally occurring, vitamin-like coenzymes. To test them, researchers used the SAMP8 mouse strain. These mice are uniquely bred to experience accelerated physical and cognitive aging, mirroring the natural decline seen in humans. In the first experiment, scientists gave the fast-aging mice a continuous supply of either PQQ or IPQ, starting from their youth, maintaining this diet throughout their entire lives. This chart shows survival curves over time. The red PQQ and green IPQ lines stretch significantly further to the right than the blue control line. PQQ prolonged 75th percentile survival by 73% and IPQ by 36%, delaying midlife mortality. The physical appearance of the mice on these supplemented diets remained noticeably younger as time passed. Looking at these photographs comparing the mice at 9 months of age, the physical proof is distinct. The control group shows severe hair loss and a coarse coat, while the mice getting PQQ and IPQ retain thick, pristine white fur. Continual exposure to these coenzymes stalled the mammalian biological clock, pushing the threshold of severe physical decay far into the future. The first experiment proved efficacy with early intervention. The next test was far more demanding, discovering if these compounds could still work after physical decay was already underway. Researchers initiated the second phase by taking a new group of mice and withholding the compounds until they reached 7.6 months old. In the SAMP8 strain, this is the precise age when natural physical decline rapidly accelerates. To measure the physical impact, the scientists utilized the 4-limb hanging test, an assessment designed to benchmark a mouse's neuromuscular endurance and overall grip strength. This graph tracks the 4-limb hanging test over 12 weeks. Notice the upward spike of the red PQQ and green IPQ lines at the 6-week mark. While control mice steadily lost grip strength, the supplemented older mice maintained and improved their muscle function. The recovery extended beyond skeletal muscle. As mammals age, excess fat rapidly infiltrates the liver, compromising internal organ function and accelerating systemic frailty. These images reveal how the intervention reduced liver fat. The left control sample is filled with white lipid buildup, while the right IPQ sample remains healthy pink. The data quantifies this. The control liver had 15.6% lipid droplets. The IPQ group dropped to 1.3%. IPQ achieved this internal cellular cleanup without forcing the liver to alter its baseline levels of mitochondria or oxygen consumption. By introducing these compounds at midlife, the research successfully reversed the trajectory of decline. These compounds actively rehabilitated failing neuromuscular and metabolic systems that had already begun to shut down. The study outlines exactly how PQQ and IPQ function as biological shields for our neuromuscular highways. By protecting the vital communication lines between the brain and the muscles, they prevent the physical disconnect that causes frailty. This graph illustrates the critical distinction between lifespan and health span. While total lifespan simply measures how long an organism is alive, health span measures the portion of that life spent free from debilitating disease. By preserving physical strength, the research demonstrates a method to maintain independent function in our later years. While these molecules successfully bypass the translation gap that stops most compounds from working in mammals, clinical trials on humans remain the final and most rigorous scientific hurdle. But this data proves that the timeline of physical deterioration is not entirely rigid. With the right biochemical intervention, the decline that begins in middle age can be halted and even reversed.